All right. Hopefully you can see my screen, right?
Yeah.
All right. Good. So I mean, this week spent the first 40 minutes just talking about student post Keras, which we won't be doing. You know, he translates this some of the Fast.ai stuff into Keras, doing what he wants. Turns out to be a lot more code than Fast.ai's three-liner, and you know, he went through how to download data from Kaggle, the command line, and how to submit data to Kaggle if you're entering a competition. So there's no real homework there unless you download stuff, but you can always go download it using their UI. And the other thing is the big chunk is on the Excel convolutions that he does there. So so catching up to this part would be pretty easy, I think. It's just watching a video. Anyways, so I think just based on our poll last week, I think the pace seems to be okay for everyone. So we have this week and next week. And then after that, we start the live course. Who knows how faithful he will stay to the existing videos. But we'll see. One thing I did want to share with you is, you know, where I go to, you know, get the latest and greatest on deep learning or machine learning. And these are my three favorite institutions. UCLA, Institute of Pure and Applied Mathematics. This is their YouTube channel. And if you go there, if you look for a playlist, Graduate Summer School 2012, and I know that sounds really old, but it's very theoretical. And there's a new one. They had a new one recently, 2018. Deep learning techniques. But you know, they have some good, like I think Stephen Mallah, he does a lot of research on wavelets and how you can analyze some of these neural networks mathematically, not just by simulation. And here, I think, you know, here they get the big speakers, you know, the main guys, Jan LeCun, Jeff Hinton here, and stuff like that. So that's one. I mean, here there was like a full summer school. There's probably, you know, 10 to 20 videos or lectures available. Another one of my favorites is UC Berkeley Simons Institute for Theoretical Computing. They get really, really theoretical. So not sure how interesting that you're into. But if you're into, like, you know, just the engineering stuff, then Paul Allen from Microsoft, I think I might have mentioned this. He has a bunch of, he has like 3 institutes, and here he has an AI institute, and they focus a lot on natural language processing. So those are my favorites. I just thought I'd share.
Yeah, by the way, I subscribe to a few different archive.org groups. I'm not sure what they're called. I forgot. Do you know about that? Yeah.
No, I just download stuff from archive. I never tried the groups. What's that like?
Well, I don't know if group is the official word. I mean, it just means, you know, there's a CS, there's a math, there's a physics, there are different sections of archive. And within each section, you might have subsections or groups or whatever they're called. So you can send them an email and subscribe to a particular section, and each day or each week you get a mail from that section, you know.
Okay. Oh.
It's a bit, right now I get a list of about, you know, 4 dozen papers with each of them has an abstract. I kind of just look at the titles and see if anything looks interesting. Maybe briefly look at the abstract, and if I want, download the paper.
Is that 4 dozen a week or a month or what?
I think you might Well, I'm getting that every weekday. You might be able to determine how often you get it. I forgot.
Okay. Yeah, I know. I think Archive has like 60,000 computer paper articles on computer science, and that's really information overload. So Andre Karpathy did it like a small little search engine for CS stuff. Yeah, and you know, for just that thing. I think using machine learning and natural language processing, of course.
Yeah.
Yeah, it's called Archive Sanity.
Come again?
It's called Archive Sanity. The
Oh,
search
Archive
engine
Sanity.
that-
That's right. That's right. Yeah. Yeah, but I read really slowly, so and my lips move, so I just tend to watch videos.
Yeah, I heard that interview with Jeremy and Sam. Jeremy's opinion was, different people have different opinions. He seems to think it's rather than in depth, look at one or two papers, let's say, and not really pay any attention to the other ones. He thinks it might be better to sort of at least briefly skim in some way, 100 different sources, so that you're getting an idea of kind of what's out there and what people are working on, even if you don't go into depth in most or all of those. So I don't know. I'm trying to get an idea of what's going on, and I know there's so much information out there. It's hard to focus sometimes.
Yeah.
By the way, also Jeremy, he said that from scratch, version 1, Fast.ai library was rebuilt from scratch. So I'm not sure how much of what we're seeing in the videos now this month will carry over coding wise into the V1 library. I wonder.
Yeah, well, from scratch could mean he's keeping the interface, but what's underneath each of those functions, the fit function or the the from data or from CSV function, that function call may still stay the same. We only really learned like 3 lines of code, right? Or maybe 4: LR find and fit and from loading data from CSV or from folder, so
yeah, that's
okay
true.
if that gets a little different. It's only 3 lines of code. But
Yeah.
I think when you're writing a library, if you're telling somebody you're doing it from scratch, most time it's it's what's under the hood that's being redone from scratch. But the interface is what we usually deal with, unless you step through some of that library, which I did a little, but I don't mind if it changes. Yeah. Yeah, so what was part of that library? I'm glad Sam asked him the question of, and I think we talked about this last week. Unsupervised, what's missing? We've basically been doing supervised learning. What's missing is unsupervised or what is it? Reinforcement, right? And in the IPAM video, Jan LeCun gave a little talk, and he said basically, I think Sam also mentioned the Jan LeCun's cake analogy, right? If you look at the whole body of machine learning or neural networks as a cake, then the bulk of that cake, the spongy cake part, is really unsupervised learning. That's how humans learn. That a baby learns most of the, a lot about the world, about the physics of the world from when from 0 to 12 months old, right? When they're just a year old, and that's pretty much all kind of unsupervised learning. They learn how to navigate the world, the robotics and all that stuff. They even learn, they can count too, and they learn that just all by unsupervised learning. They have number sense. So that big body of work is not there in Fast.ai or in a lot of libraries yet. It's not really well explored.
And in fact, I was a little disappointed by Jeremy's answer to Sam regarding reinforcement learning. Well, it was an unexpected answer where he said that he's not convinced reinforcement learning people really know what they're doing, since they're just pretty much just throwing a bunch of hardware at different problems to see what happens. So he's not interested at the moment to include reinforcement learning in Fast.ai. That might change in the future, but I guess that's his view now.
Yeah.
Yeah, I think that's pretty much in line with the Jan LeCun also saying that the reinforcement learning is pretty much, it's needed, but it's only a little bit, and it's like a cherry on the cake. Whereas the bulk of the work is the self-supervised learning or the unsupervised learning. That's what's a bit, I guess, a bit lacking at the moment in the deep learning zone.
Yeah. There's also a lot of other stuff. I mean, what we're learning is, you know, we're just, of course, we're scratching the surface being course one, but in another one of Jan LeCun's talk here, he lists all the stuff that all the other people everybody's doing now. They're basically, you know, combining different networks together. They have networks creating networks. They're doing, you know, question and answering tasks and a lot of other stuff. I think, you know, reinforcement or even I guess GANs, generative adversarial networks. You know, they're just different networks interacting with each other. So what we're doing now is just we're focusing on a single network type. So yeah, there's a lot more. But, all right. Anyways, so I don't know. You know, as usual, I got a little confused throughout the lecture. So I'm going to talk about what I delved in. And does anybody have anything else they want to talk about?
Well, now with the V1 library, it's a little bit, could be confusing how to run the old course, no, or 0.7. Maybe that's a good topic for discussion. Like if anyone's kind of confused how to now run the old course. I was a couple of times.
You mean like you downloaded the V1 library and is that?
Yeah, for example, if someone was using Kaggle kernels as I was for a while, and then the Kaggle updated the library to V1, like initially on CPU and then on GPU. So for a while it was running on GPU, but then now it doesn't run. So you have to do like downgrade to 0.7 if you want to use Kaggle kernels and the old course. I don't know how other, like Paperspace, what you have to do to run 0.1 versus 0.7. I guess if anyone's got anything to share in that respect.
Has anyone tried the version 1 yet? Besides Mikhail? I haven't. I'm just waiting for the first lecture and then he'll tell us how to install it.
Yeah, I'm waiting for it too. I think on the forums I saw Salamander gives you an option in the drop down to select Fast.ai 0.7 and Fast.ai V1.
Salamander, is that like a VM vendor? Or?
Yeah, it's like built on AWS. So in the V3 forums, there's a separate topic for Salamander on forums.fast.ai. So in that, from the drop down, you can select whether you want to work on Fast.ai post 0.7 or Fast.ai V1.
I see.
Yeah,
well, it looks like Salamander makes it easier.
Yeah, it seems like a lot of guys upgraded to 0.1 to version 1 library.
Yeah,
so, yeah.
I think if I'm running Docker, so I may just like do a separate Docker image for it.
Right, so it's easy for you, yeah. Like Kaggle kernels was a bit messy during that change. All of a sudden the code stopped working, so you had to downgrade that to 0.7. So it seems like with pip install Fast.ai equal 0.070 it works, but yeah, that took me a while to figure out how to do it, but it's fine now.
Yeah, well, luckily, I guess this week's half lecture, you don't have to do much homework, so.
Right. I don't know how like Paperspace, I didn't try it, but I know like Google, they've updated 2.1, so I'm not sure how do you go to 0.7, so I guess there's a way.
Google 2, which part of Google 2.1?
I mean, the Google Cloud Platform, they also announced support for the library, so I guess that's 1.0. So I guess if you want to run 0.7, you have to do something extra, but I didn't try it yet.
Okay.
Mm-hmm.
In the chat, I've pinned the link to the thread on Salamander.
Oh, okay. Oh, yeah, I should probably check chat somewhere. Let me see what's going on with the chat. All right, thank you for that link. Cool. Let's see. Okay, well, I'm not going to log in right now. Anyways, so this week we're talking a lot in a lot of detail about the convolution. He has that Jeremy showed that video from Octavio Good of the convolution animation. That's a really cool video. One thing, all this kind of bothers me. What bothers me about all this is coming from, neural network, the machine learning, deep learning is supposed to take their inspiration from neural networks, which is biology, right? So how does all this map to our visual system, our brain, right? And so the core of convolution, when Jan LeCun introduced it like decades ago, was the concept of shared weights, but in biology, there is no such thing. And I think what I mentioned before is you can interpret that as saccade. So let me kind of scroll out. Okay. So let's say you have, and where is this? Let's say you have this image here, and this is your first layer of neurons. I think here's layer 1, right? You have three sets of convolution weights here. These are the 3 dots indicate. So this guy here is going to look at a small patch of image here, of course, and then the convolution means you step over, you take a stride of maybe 2, you look at this patch and so forth, right? So looking at the first patch gives you some sort of activation, maybe an activation 2, and then the next step you get an activation of 4 or something like that. So so each one of these steps, according to convolutions, Jan LeCun's convolutions, is supposed to be a separate neuron. They have like, say this is a 3x3 convolution, so they have 9 weights. And so there's another 9 weights here, 9 weights here, but all the weight values are the same. So that's the concept of shared weights. Of course, this does not exist in. So actually, Jan, even there, let's say your array here is 10 by 10. So you have 10 times 10 times 9, which is 900 weights. In truth, the 100 of them share the same weight, so it's really 9 weights. But that's the way, yeah, I'm sorry. Yeah, you have 100 neurons and 9 weights according to Jan LeCun. So, but there's no such thing in biology, and you know, so a lot of times we say, well, who needs biology, right? You know, we got along just fine, you know, doing von Neumann machines for the past 70 years, and okay, well, and you know, biology, you know, we got along with it just fine with databases and the internet and stuff, but we got stuck on some problems like pattern recognition. So sometimes we need biology, who knows? And even now, like a lot of the unsupervised learning stuff, I mean, we're still kind of in the dark about that. So, and that's to me, and maybe to Jan LeCun, that's a huge chunk. That's the spongy part of the cake, right? And that's like 80% of machine learning to me. So maybe we need some more inspiration from biology. So for that, we got to map all this engineering stuff we're doing back to the biology somehow. So there's no such thing as shared weights. So what the way I see this as, what we have here is 3, you know, layer one, and there's, you know, there's supposed to be 100, so 300 neurons here, according to Jan LeCun. But the way I would interpret it from biology is that there's only really 3 neurons. And what each neuron is doing is it's sweeping. Let's call this neuron A, neuron B, neuron C. What neuron A is doing is it's sweeping across this image, right? It's making the sweep. And it will generate this layer here that you see. And the activations that it generates will be that layer, this sheet right here. So, and you know, there is evidence for that, slight evidence that that we do take a sweep across that, and that's called a saccade, right? Our eyes just randomly move about, like probably multiple times a second, sweeping the visual field, right? That's a saccade.
So you're saying that when light enters your eyeball, rather than that one piece of light being viewed by multiple neurons, it's the other way around, maybe, where one neuron is looking at multiple photons, multiple pieces of the light.
Yeah, multiple pieces of the retina, because each light hits the retina. Yeah, that's kind of like what I'm saying. That's what I'm proposing. So I think I mentioned this before, all this before. But so in this lecture, we're getting deep into, you know, how these convolutions are actually working. So the other thing, so I'm going to carry this analogy a little bit further. The other thing is that there's biases here I haven't talked about, right? Biases. You know, your what is it? WX plus B, right? That's your sort of like your activation. Of course, you put it through a ReLU, and so there's these biases. So each one of, you know, I have to, you know, in the biological interpretation, you know, each one of these guys here, there's like 100 biases on this first sheet, right? There's 100 biases according to Jan LeCun. And, you know, is there 100 biases in, what's that equivalent in biology? And, you know, your eyes are not going to sweep, you know, when we're taking these convolution steps, we're taking a stride of maybe 2 or 1 pixel, you know, we move over every 1 pixel, or a stride of 1, or a stride of 2, or a stride of 3. Well, your eye isn't, you know, it isn't scanning the world like that. It's like I said, it's only taking probably a few 2-3 movements a second. So it's gonna, so each one of those image captures, maybe let's call it 3 image captures that your eye is doing, they have their own, I'm gonna say, you know, make believe they have their own biases. So there'll be like 3 biases there, not 100 bias as we have here. So that's how I would interpret the biases there. And there's kind of, I think recently I read evidence that your neuron can see multiple things at once. It has like multiple channels of input. Not talking about the synapses. You know, your neuron will have 1,000 to 10,000 synapses. A synapse being a weight, but it can kind of like see multiple things at once, independent channels. So I'm going to guess that might be a bias. Those independent channels are different biases. So a neuron can have multiple biases. So that's how I might interpret that. The other thing,
Sebastian, could you translate that into changing the approach, taking a more biological approach? Like if you had multiple biases, how would, there'd have to be something different about them, I guess, in the training procedure to set those values, to optimize them.
Yeah, well, I think the thing about my interpretation of this is that it still works, computationally, what we've been doing all along still works. If we just pretend like the neurons have 100 biases and they sweep, the biological neurons are doing a stride of 2 sweeps across the visual field. So that all, so our algorithm here is still consistent with a biological interpretation, except we just don't call these things 100 neurons here anymore. We just call them 1 neurons, and they're taking 100 strides. That single neuron is taking 100 strides. So our algorithm is still consistent with the biology. It's just the way you interpret what a neuron is that I would change. And yeah, and in terms of training, now if you want to really carry it a little further into the biology, then you have to do it so that we only need 3 biases now instead of 100 biases, right? So I don't know how to do that. I don't know if that works. So, my biological interpretation can break down there, but yeah. So now, if you're looking at now let's go to multiple layers. So you have your picture here, down here. You have your first layer, layer 1 here. And then let's take a look at what layer 2 is doing. So layer 2 is taking a patch of neurons. Let's say another set layer. I don't know if I'm. Let me do a new one. Okay, let's go back. Here's our image. And here's our 3 neurons. And it generates this activation map. By the way, this, they call this activation maps or feature maps, right? Let me get some vocabulary clear here. What is a neuron? For me, a neuron is equal to a feature map, or it generates a feature map. One neuron generates one feature map. One feature map, which maps to actually equals is not the right term. Let's just do arrow. Which maps to one kernel. It's created by one kernel, and it's created by a kernel is the same thing as a set of convolution weights. Let's say in our 3x3, Okay, so that's what a neuron is. It's a feature map. A neuron generates a feature map. It's a convolution kernel. Okay, so this is back to. Let's go back to layer 1. So that's layer 1. Now layer 2. Here's layer 1's A, B, C neuron. And layer 2, what this part of the feature map is looking at is, let's say, this patch of the feature map, or this partial segment of a neuron. But it's also let's see. But it's also looking at neuron B's 9. I can't call that really pixels, 3 by 3, and neuron C's 3 by 3, right? So this one neuron's looking at that whole set A, B, and C, that part, and it's summing up the activations for A, B, and C. But so what does this, what is this guy? How does that translate to what it's seeing in the pixel space? Well, first of all, let's look at the connectivity of layer 2. Here's neuron. This let's call it the Z neuron here. Let me go backwards in the alphabet. Y neuron, and etc. Right. So this Z neuron is actually fully, since it's looking at all A, B, and C, it's fully connected to the layer 1. It's connected to all neurons here. I know that sounds weird, but because it's only looking at a part of that feature map space, but since all the neurons A, B, and C, it's doing the convolution with all of them, then it has to be connected to all those neurons. In the lecture, in the Excel spreadsheet, we have our last layer of neurons is like a fully connected. He says he has a fully connected layer, right? And but that version, that meaning of fully connectedness means it's fully connected to the feature map, every point in that feature map. Whereas here, this fully connected is connected to all neurons, a partial feature map. Okay. Sorry for the chicken scratch there, but so if you want to bring it down to the biology, then to interpret our convolution network, we would have to say that layer 2 is kind of fully connected to layer 1 in the biology interpretation, not in our computational interpretation. Okay. So that's what the layer 2 to layer 1 connectivity would have to mean to me. It's a fully connected with all the wiring of one neuron connected to all the neurons of the previous layer. Anyways, so I don't know if there's anybody with a biology background here, but maybe they may have a different interpretation. But that's the only, this is how I keep my sanity. Like when a biologist looks at this, and if you're talking about shared weights, that's like an engineer listening to a biologist saying like, oh, one file is equal to one disk block. It's almost that absurd. A file is spread among thousands and millions of disk blocks, not one. So that's the shared weight idea is that absurd in biology.
In that layer 1 you've drawn, I guess that has a much smaller vertical and horizontal dimension than the input image, if you have a 3x3 filter or something like that.
Not
Right.
that much smaller, because let's say your input image is maybe 100 pixels, right? That's 100 pixels. And then, so if you're taking a stride of 1 on each convolution, your convolution width is 3. Your kernel width, so you have a 3x3, right? So this width here is 3, and you're taking 1 pixel steps. So you're still taking like 97 strides, right? Steps. So the width here would be like 90. So you're getting 98 activations. So you're going from 100 to 98. So it's not much smaller. Now, what makes it smaller if you're taking like in a 7x7 convolution, and you're taking a stride of maybe a stride of 2, then your feature map, the size of your feature map is going to be 7 plus, like 100 minus 7 over 2. So you're basically, the stride 2 is really kind of halving that. So that's when it gets smaller, is when you take bigger strides.
And also with max pool layer, for example, right?
Right.
I'm wondering, would there be any biological notion of that kind of decrease in dimension?
Yeah, I don't know how to. Well, just the concept of you're going from one layer to the next. I'm not sure. There is, just because in biology you have the layers of the neurons. You have layer 1, these neurons here, L1. You have layer 2, L2, and it's it's going to be connected, or maybe fully connected. Then what's the size? So what we're asking is, what's the size of this feature map? Does it decrease? And I'm not sure. I have to think about it. I think it should, but well, actually, if it's in real biology, even layer 2, you don't usually get fully connected layers. I mean, you're usually only gonna get these partial connections, which is the original inspiration for convolutions, because like your layer 1 or it's called V1, or maybe the lateral nucleus, is only connected to a small part of the retina. So that's the original inspiration for convolutions. So you usually don't get these fully connected layers. There's usually only these partial connections. But yeah, I don't know. I'm not sure. I have to think about what the size of the feature map would be there. But let's go take a look at this paper we've seen before, right? How do you interpret these convolutions? And we've seen these pictures before. I kind of broke it down a little bit. So the paper is the Zeiler and Fergus. Yeah. So yeah, here's the link to that paper. Hopefully you've seen it before, but I just took 2 figures from that paper, and I blew it up because we do. All right. So here is I don't know. Hopefully you can see my mouse moving around, but the original image is on the left. The first layer, this is this 110. That's the feature map size and it's in this red square here. So what I'm showing here is that let me see. So this is layer 1 here. And layer 1, these activations, I show the square of 9 activations here, right? So each activation is looking at a 7 by 7 pixel patch, right? So these 9 activations, and we're taking a stride of 2, so these 9 squares are really looking at an 11 by 11 square patch, right? So the first one is 7 pixels. It gets you to pixel number 7. This next one here, it gets you to pixel number, you're taking a stride of 2, so 7 plus 2 is 9. The next one here gets you a stride of 2. 9 plus 2 is 11. So it's looking at an 11, this activation patch here is looking at 11 by an 11 square pixel patch. And then what you do, the next thing that happens is a max pool layer. Well, this max pool layer is doing a 3 by 3 max pool with a stride of 2 again. So so one of these activations on the max pool layer, it's looking at 9, and it's taking the max of those 9 activations, and it's taking a stride of 2. So this guy, because we said this square is looking at an 11 pixel patch, 11 square pixel patch. So therefore, this activation here is looking at an 11 square pixel patch, right? Remember, this square here is a 7 pixels. I'm just going to say 7 pixels wide. And this one here is 11 pixels wide. Okay. Next, the next step would be doing a 5 by 5 convolution to get you to here, to this layer. This is layer 2. So in layer 2, you do this 5 by 5 convolutions. That's what this little green square here is, right? That's a 5 by 5 convolution. And so it's looking at these 5 wide activation patch. Now this, if you go through the same kind of rigmarole, you have to, each one of these pixels, each one of these activations is 11 pixels. I'm sorry, 11 activations. Each one of those is what?
Yeah, I guess you can say that each one of those is getting information originally from 11 pixels of the original image.
Well, 11, actually, it's getting, I think if you go through it, it's getting a 27 pixel patch. So it's 27 wide.
One step before in the previous step, I think it was 11.
Yeah. Well, this guy is looking at 11, but then this guy is going to be more than 11.
Yeah.
It's 27 actually. And then you go through the same kind of thinking process. And one of these guys, I think Zeiler said in one of his videos, the author said it's 80, roughly 80 wide. I haven't done the calculation on this. So now let's go back and verify that this is a 27 wide pixel. This guy here is an 11 wide pixel, and this guy here is a 7 wide pixel. The 7 wide pixel is obvious, right? That's why so what are we looking at here? What we're looking at here, So this is 7 wide. This guy here is 7 wide. It's what we have here is 9 convolutions, 9 kernels. Let's call it 9 kernels. Okay. So this kernel here corresponds to these input patches here, right? So these are the 9 input patches that activate this kernel strongest. And so if you zoom in and if you count these pixels, of course, this is layered 1, it's easy. This guy here is 7 wide, right? So if, what I did was I zoomed in and I counted those pixels. Let's see, view. if you take the original paper, you zoom in, you count those pixels, it's 7 pixels because, go back to the original papers and do that is what I would suggest. Zoom in on that. And then if you, so that's layer 1, that's easy. Layer 2, what we're looking at here now is, let's see, let's zoom out. I believe this one is one kernel. And what strongly activates those kernels are these image patches. So, oh, I'm sorry. Yeah. So let's see. Yeah. So we're at layer 2. We have a single kernel here. Remember before, this was 9 kernels. These images start to look the same, but this image here is just one kernel with the 9 strongest activations shown here, right? And what is the pixel, the original, it's not layer 1. What is the original pixel that how big is the original pixel image? This layer 1 here is confusing me. That's talking about the top picture. Okay, we're at layer 2. And if you zoom in on these guys and count the pixels, it's 27 pixels. So therefore, that makes me think that these little, pixel counting exercise that I did might be correct. There's 27 pixels there. He didn't show one where with the 11 pixels. He didn't show that. He showed in the article. He showed that, and he showed this layer. That's the layer 1 neuron right here with 110. 110 being like the feature map width, and layer 2. That's the 27 pixels from the original image is what that neuron there is looking at. I hope this did not make it more confusing, but I found these, because all these pictures are kind of like 9 by 9 squares of something. I thought it was confusing. So I went back and I blew up the picture, counted the pixels, and it seems consistent with everything.
So when you say 27 pixels wide for that layer 2, then no other pixels outside of that 27 by 27 patch in the original image has any effect on that kernel in layer 2, right?
Well, it has any effect on this one activation?
Right.
Yes, you're correct.
Yeah.
Okay. And there's more. There's a little more to it. Oh, there's one more thing that Jeremy mentioned. Is that he mentioned that these convolutions can be high dimensional, and just looking at the way these things are computed, I'm not sure if that's true, because these convolutions here, you're looking at let's hopefully you can see this, but this little 9 by 9, 3 by 3 is really 2D, right? An X and a Y. And there's another dimension in going to the number of neurons, because if we're looking at this, we're looking at only one neuron. The third dimension is down the number of neurons, remember, or feature maps, remember? There's more of these, there's 96 of these here. So that's your third dimension. And it's not like 12 dimensional where you have to say 2 dimensions and 2 dimensions, 2 dimensions, 12 times like he was saying in the lecture. So it looks like what's here is 3-dimensional kernel. And then if you have, someone mentioned maybe the batch adding another dimension into it, a batch size or batch width, or batch count. I'm not sure, but at most 4 dimensions, not like more than that, I don't think. So that's all you ever wanted to know about convolutions, I think. All I ever wanted to know. All right. I think that's all I really had to say this week. if let me just throw it out there again. If anybody finds a topic that they think is interesting, that they felt needs to be explored some more, please feel free to enlighten us. It doesn't have to be a polished presentation or anything like that. Just, you notice I do a lot of scribbling. So yeah, we'd love to hear from you.
I have a comment, general comment. You're talking about, biology and some interpretation, and maybe we can, even make some changes possibly based on the biological interpretation. There are other types of problems, right? That, I mean, in one sense, there are two types of machine learning, maybe you could say. You could break it down in different ways. In one way, there are those that you're trying to be as good as a human, and then you'll be happy, or maybe even better, like language ability or image object recognition. Really, you want to try to do as good as a human brain. But there are other things like fraud detection, for example, where humans are horrible at looking at a string of transactions from somebody's credit card over and over again, and then all of a sudden identifying something that looks like fraud immediately. There are a lot of things like that where we're designing algorithms where humans, it's extremely easy to be better than a human. So I guess deep learning now is focused mostly on the first category, where we're just trying to mimic what the brain is doing and do as well as the human brain. Just one way of looking at things.
Yeah, I think you're right. Well, I mean, we're horrible at time series or fraud detection.
Or even like finding the best fit, straight line fit to a cloud of data points. We can't do that accurately, very accurately, but for computer, it's easy to use a regression to do it perfectly.
Yeah. I mean,
yeah.
I think there, even though I think computer science sort of like, I'm not sure what it is, bastardize or violate a lot of the inspiration it took from biology. It's still very useful. Yeah. All right, with that, I think I'm going to end a little early today. I gotta go out of town, but hope you found this useful. And I think the next part of the lecture is going to be extremely interesting. I think he's going to talk about databases. And that's the most boring thing in the world, but how do you apply machine learning to database data? So it's I think it's called embedding or something. But yeah, so
we won't get to video 4 in this sequence this month, right?
Right. Well, yeah, that's correct. We're going to end with video 3, and then we're going to start off in the live course.